Jr. here, back for some more science, some physics. I'll be moving all of my science stuff onto this channel, so it'll be properly a STEM channel. On my other channel, I'll probably still mention science stuff from time to time, but it won't be any in-depth stuff really. I had the Science Hour show. I'll move that here as well. So y'all get some Science Hour. You'll get some theory and concepts, get some problem solving, get some reading of textbooks. So we have that going on. So what I plan on doing today is actually getting some quantum mechanics in. I'll be starting graduate school in the fall, and I'll need to be able to, um, understand the undergraduate quantum stuff very well. Quantum is my weakest subject, so uh, therefore I'll go ahead and try to maximize what I'm doing with it. So what I'll do, I'll actually pick up from where I left off before uh, in the textbook. So last time we were on chapter 1.4. I guess I'll go to boom, here we go. So last time we did this uh, on my other channel, that is basically doing the derivation for the how the normalization doesn't change with time, because the derivative with respect to time of the integration of uh, the density parameter over all of space equals 0. So therefore it doesn't change with time. So that means it stays normalized over all time. That's what this section is talking about. And I wonder, should we take and look at this problem here? It gave us two different problems. We will check out this first one. So this was a derivation where the kind of trick that the book did was pull out the derivative with respect to time here, pull it out and do it separately, and then plug it back in at the end. So I'll try to get in the habit of doing something similar. So let me see how things are situated. I'll move this over a little bit. Right. And perhaps I can also, looks like that's already maximized. So I'll actually shrink this a bit. And there we go. So let's look at this problem just to get some practice with it. So it's saying at time t equals 0, a particle is represented by the wave function. And it gives us wave function at t equals 0. A x over a for 0 less than or equal to x less than or equal to a. And we have a b minus x over b minus a for a less than or equal to x less than or equal to b, and then 0 for everything else. So I think I wrote that correctly. A x over a b minus x b minus a, 0, 0, let's see, x let's see, b. All right, that looks good. A, A and B are positive constants. So first we need to normalize by finding out uh, what A is. So we know that if we have a particle and we're getting some information about that particle, we know it's going to be located somewhere if the particle exists. So if we were to take the integral from negative infinity to infinity of psi x 0 squared dx, that will equal 1. So we can actually plug this in, and we know it goes from 0 to a, which is a x over a dx plus a to b, and that's a b minus x over b minus a dx. So we'll just keep this going. And let me actually put my pad in a more comfortable place. There we go. It's a whole lot better. So all we have to do now is do these integrals and solve for a. So this will be a over a, and that's just x. So that's x2 over 2, a0 plus. So this one is a bit more complicated with the actually it's not. So we just have a b minus a integral, and now we have b minus x dx. So this should equal a b minus a, and this should be bx minus x2 over 2, and this should be a to b. So now all we have to do is solve these two. So we have a over a squared over 2, and then the next one is going to be 0 plus a over b minus a, and this is going to be b squared minus b squared over 2 minus, for the integral, b minus a, and this is going to be ba minus a squared over 2. So you can actually extract the a out of here. So this equals a over 2 plus a plus 1 over b minus a times. So this is b squared minus b squared over 2. So that's b squared over 2 and minus 1 over b minus a. And this is going to be b a minus a squared over 2. So that's rather complicated. but I mean, it is the answer. So, I mean, this all equals 1. I mean, so we could just stop right here and say A equals A over 2 plus 1 over B minus A, B squared over 2 minus 1 over B minus A, B A minus A squared over 2 to the inverse 1. So, let me check my other channel that have something going, sending everybody here. So I'll just check briefly and make sure that's working properly as expected. And far as I can tell, everything is working properly. Even though for a second it seemed like the link didn't work, but seems to be working now. But interestingly enough, it seems like when I was doing this weird thing where it changes to a regular link, that's wrong. So give me a second. I'll put the link proper without the YouTube link update, since apparently that doesn't work properly. And all right, so that fixed it. All right, so we're looking good. So to continue with the problem, so we have that, and it says sketch psi x of 0 as a function of x. So let's look at this. So basically, the axis goes from 0 to b, and a is up in here somewhere. And a is quite ugly. So I guess I do need to simplify that. I'm going to plot it. So let's see if I can uh, better formulate the best way to simplify it. It might be just to do it. So we have a over 2 plus b squared over 2b minus 2a minus ba over b minus a plus a squared over 2b minus 2a all to the inverse 1. So here we have a few things we can consolidate. We have a over 2 plus b squared plus a squared over 2b minus a minus b a over b minus a. And if I were to multiply this by 2 over 2, then we would get a over 2 plus b squared plus a squared minus 2ba over 2b minus a. So it seems like they want us to do this, a over 2 plus a b minus a squared over 2b minus a. So you see how that works? So if I do b squared, I get this. The inner, I get b uh, times a. Outer, I get b minus a, so that's 2b minus a. Excuse me, minus ba and minus ba is minus 2ba. And then the plus a squared gives me this, which means that a equals a over 2 plus 1 over 2 b minus a over 2 plus b minus a over 2. So that equals a plus b minus a over 2. So that equals b over 2. So that's a pretty simple answer for just a complicated looking thing. But of course, they have the benefit, the people who make the problems, they have the benefit of, uh, you know, starting with a simple thing and making it complicated. So they know what it's going to be by the time they finish with it. They can sort of reverse engineer the complex thing. And, we don't see the simplicity behind the complexity until we work it out. So now we did this so we can graph the thing. So psi x0 now equals a is b over 2. Hold up, I forgot my inverse 1. Equals 2 over b. All right. So a is 2 over b. So we have 2x over ab for 0 less than or equal to x less than or equal to a. And then we have, so that's 2 over b. So that's 2b minus x over b minus a for a less than or equal to x less than or equal to b. And everything else is 0. So that means that it's 0 out here, 0 back there. 2x over b, 2x over ab. So this is not necessarily easy to graph. Well, AB is a constant. So basically it'll be a straight line. Like if there was no constant underneath, it'll just be a line like this with a slope, I guess, of 2. But the denominator is going to make it smaller along the way. So perhaps it's something like this. Because A and B are constant. Could be wrong about this graph, but this is what I would do given what I have here. And the next one is a whole lot more complex. B squared minus BA. So essentially the denominator is constant as well. So just looking at the numerator, we have B minus A, which will eventually hit 0. So we know that at B it's still 0 here. And when B equals A, that's the maximum is going to be. And X is changing in a linear fashion. I mean, it seems to be like this. Right, that's what I would say the graph would be. So what I'll do is actually go to an online calculator and see if I got this right. Right, so the 2x over AB is right. I need to make A and B different. And I'll put this image on the screen momentarily. Yeah, so looks like I got it right. So give me a moment, I'll put this image on the screen. Thank you for watching. Who's watching at the moment? Be sure to drop a line, say hello. So this is section 1.4. I guess I'll just say problem 1.4 graph. Almost there. All right, there we go. So looking at the graph of the problem, here I have a equals 2, b equals 4, and you can see that when a equals 2, b equals 4, we do have from 0 to the red line is 2x over ab. So from 0 to a, which is 0 to 2, we see that works. And then the line from the blue line is 2b minus x. The 2 gives the magnitude of the slope. The b minus x gives the downward slope. And it's interesting that the b squared minus ba inputs the same degree of decrease as the left side. So quite interesting how math works. So that's that. And I'll put this image. All right, there we go. All right, so let's see what we have next. It says where is the particle most likely to be found at t equals 0? Of course, that's going to be at a. So graph in the, at least I believe that's the case. I wonder, should we do the integral to be sure? I mean, I would guess a, but this is a graph of psi, not necessarily the probability density. So think about that. I just realized something I didn't do. I didn't actually square everything. It was so fun too. There is no I, so I have to worry about that. So what would happen if I squared everything? Thanks to who's watching. Be sure to drop a line, say hello. Thank you for watching out of the way. Actually, I'm going to leave this there because that was done so nicely and so fun to do. But I'll go ahead and copy it because I realized I forgot to square it. So let me square it and see if something else happens. My gosh, I have so many extra pages in here from, it seems like whenever you copy paste something or something like that, it adds a whole bunch of extra pages. Slightly aggravating. So let's see what happens when we square this thing. See if it gives us something different. It seems like it should. So basically, it'll be this squared, this squared. So you'd have a squared over a squared. And then you would have x3 over 3, a 0. And then you'd have a squared here and this squared. And then you'd have this squared. So that definitely does complicate things. So trying to see if I can um, let's try my best to multiply it out. So I'll do that. And I'll come back to this. So you would have a over b minus a squared, integral from a to b squared uh, minus 2bx plus x squared dx. So then we have plus a over b minus a squared, and although this times x b squared minus bx squared, when divided by 2, the 2 goes away, and this is going to be plus x cubed over 3 and ba. So let's see what we end up with now. So we have a over b squared, a cubed over 3, and this one's going to be 0, plus a over b minus a squared, and I'll try to do this in one line. We have b cubed minus b cubed, and make sure that's correct. Looks like it. Plus b cubed over 3 minus a b squared plus b a squared minus a cubed over 3. So because of the integral, we have to subtract the a variables. So I'll put a minus on the second one, a plus on the minus on the first part of the second one, a plus on that one because it'll be minus a minus. Then minus the last one, plug in the a's for the x's. So that seems right so far. If I make a mistake anywhere, let me know. So then we have a over b squared, a cubed over 3 plus a over b minus a squared, and hopefully this simplifies as nicely as the previous problem. Doesn't seem like it though. We have b cubed over 3 minus a b squared plus b a squared minus a cubed over 3. So again, this seems quite complicated to simplify, but I'll learn from the first iteration that it must be some trick that ends up simplifying it for us. So let's go ahead and distribute everything and see what happens. So in this case, now we have a squared on the outside. So then we have a cubed over b squared 3 plus, and the a squared is taken out. So that's b cubed over 3b minus a minus a b squared over, that was a squared, over b minus a squared plus b a squared over b minus a squared minus a cubed over 3b minus a squared. And as anticipated, it does seem to be offering us some ways to simplify pretty easily. So we have a cubed over b squared times 3. So this is going to be plus b cubed minus a cubed over 3b minus a squared. And that's these two here. And then we have plus b a squared minus a b squared over b minus a squared. So we're going to do something similar to last time and multiply everything in this case by 3 over 3, at least for that one thing right there. And technically, crap, I have to multiply everything again by b squared. I have to consolidate that first one, which I can do. It just takes I have to make some room. So I did b squared, b squared. And then we have b squared over b squared. So then we would have b minus a squared, b minus a squared. So looking at this, the denominators are the same. So you can just plop that there and call this 3b squared, b minus a squared. And for the numerator, it's quite ugly. We have a cubed b minus a squared plus b cubed, actually b fifth, minus a cubed b squared plus 3 b a squared minus, actually I could just distribute that, 3 b cubed a squared minus a b to the fourth. quite ugly. That's a very ugly A. So I'm going to solve for A here. That'll be the inverse of that. And let me check, make sure I'm thinking of this properly. Yep. Sine squared. Yep. Sine squared equals 1. That's just quite ugly. I made an error on the integral somewhere. But yeah, I didn't feel like continuing with this simplification. Um, I mean, I could distribute the 3 on the end. That's pretty ugly right there. Check one more time, make sure I didn't make a mistake anywhere with my squaring. Good. Oh, I see what I did. No, no, never mind. I got that. I was thinking, oh, when I looked here, I forgot to square the x, but the x was squared. That's how it became x cubed. Well, we got the general concept. So this seems to be just tedious. But the main concept here is the probability density will give us the probability of finding a particle at a certain location. And I think my mic is sagging again, or I was just leaning down to speak. Right? So the idea is that probability density that allows us to get the probability of the particle being at a certain location. And I'll turn the gain up just a little bit. You know, in those cases, you got to turn the volume down some. Gain is going up a little. Gain is going up a little. Right. So hopefully that's better. It was a bit low. So the probability density allows us to find out the location of the particle within a certain probability. So all we have to do is basically integrate the probability density from negative infinity to infinity, which when you have psi, is going to be psi squared. Uh, if psi squared includes an a, just remember that from negative infinity to infinity, the probability density will always give us a value of 1, because the particle will be located somewhere. And if you wanted the probability of the particle being at, let's say, between a over 5 and a, then basically we just integrate the probability density over that range in order to give us the probability of the particle being between a over 5 and a. And if we were to separately um, do all the integrals, you know, for the probability density along the entire range, and so on and so forth, then it'll all still equal 1, or 100% probability for being found. Well, that's the main concepts. Either there's some incorrect on the math or it's just tedious. So I won't keep doing that one. Let's go to the next section. Actually, I'm going to save the next section for next time. So it's a few pages. So what I may do is come back tomorrow and we'll do a reading one where we go ahead and read through the momentum section and get a some understanding of momentum as far as the quantum uh, description of it. So hope you all enjoy. I may pop on a few times throughout the week and do a little something here and there. I'll definitely be here Saturday night to do a science hour show. So be here for that. I'll continue the numbers from the previous channel. So and the other channel's still there. The previous channel where it was at. So I'm on like show number 20 something, I believe, 30 something. So if you want to see the previous ones, just go to darrellleberryjr.com, go to the personal YouTube channel that's there, and you'll be able to see the previous ones. And then you can come here every Saturday and see the ongoing ones. So thanks everybody who popped up for watching. Be sure to like, subscribe if you haven't already. Let me know if there's a subject you'd like me to tackle. I may actually look into some classical dynamics, classical mechanics again as well, because I'll be taking that class in the fall. I actually did pretty well in that class, but I still want to make sure I stay refreshed on it. So, and plus that allowed me to get to chapter 2 or 3, one of the chapters somebody wanted me to cover. So thank you all for watching. I'll see you all tomorrow most likely, and if something comes up, I'll definitely be here Saturday. But I'll try to make a point to be here sometime tomorrow, and it'll have to be earlier before I head into work. And we'll see how that goes. I'll play it by ear, as they say. All right? So thank you for your time. Have a good one.